We will kick off then. So thank you everyone for joining us for the second base pair genomics webinar, where we're diving more into using GBVs and looking into further details of what GBVs can do for your herd and what it all means in the larger context. So today we're very lucky to be joined by Professor Ben Hayes, who is the man behind GBVs and behind actually genomics in Australia, I believe. Ben can correct me in a moment if he needs to. Ben was previously the director for coffee at UQ and is currently the research director for the Zero Net Emissions CRC, which is a big project that's starting to kick off now. So Ben, would you mind telling us a bit about how you got into genomics or how you started genomics?
So to go back to the very start of genomic selection, I was lucky enough to be down in Melbourne after I did my PhD in Rockhampton with the beef industry at the time. And then in the late 90s, I was down in Melbourne working with the dairy industry. And I was working with a very esteemed geneticist, Mike Goddard, and a colleague from Norway, a friend, Theo Mewison, came over. And I was just lucky enough to be involved in it was really coffee conversations at that time on if it was possible to genotype a lot of DNA markers across the genome, how would you actually use them? So that was really the origin of genomic selection over a couple of cups of coffee. We did publish a paper on that in 2001. But the interesting thing looking back on that, at that time, it was completely impractical because we were saying you needed 3,000 markers across the genome to make these genomic predictions of, in that case, it was milk production and other dairy traits. You needed 3,000 markers. At that stage, it cost about $2,000 per bull to genotype for those 3,000 markers. So it was completely impractical. But anyway, as good theoretical people, we published that paper. And then in about 2007, 2008, the SNP chip technology that we're all so familiar with now really came out, driven by companies like Illumina. And it was actually nothing to do with cattle that drove that technology. It was all about genotyping people so you could predict diseases and diagnose genetic risk of diseases. But we saw that developing technology and we thought, hey, that's exactly what we need to get genomic selection up and running. So in about 2008, we started really seriously implementing that in dairy cattle. So we genotyped a large reference population of dairy bulls that had lots of daughters and really good herd recording. And we came up with the first genomic predictions for traits like milk production, protein, mastitis resistance, and so on. And that was how genomic selection started. And that paper was the origins of genomic selection around the world, actually, I'm pleased to say. Just shows you how useful some cups of coffee are.
All the best ideas are over a cup of coffee or tea. So,
yeah, you need to make space to have those good ideas, that's for sure.
Yeah, 100%. And then, so dairy genomics we know is quite a bit ahead of beef genomics. So how did you, I suppose, take a step back and come up into beef genomics, particularly in Northern Australia?
So dairy genomics, I'm being a bit flippant here, but in a sense it's easy because you've got cows being herd recorded a few times a week or sometimes twice a day. So you've got an enormous amount of data for your reference population. You've got one really dominant breed, Holsteins, and then you've got Jerseys and Reds. So just 3 breeds. So the path for, well, the way forward for dairy genetics or dairy genomic selection was just building a bigger and bigger reference population. And we were getting up to very high accuracies like 0.8 and so on. The challenge remained to get the technology up and working in beef cattle. So that was one of the reasons for moving. There were other personal reasons. The weather's a lot better in Queensland, of course. But the challenge of getting this technology working in our really multi-breed, crossbred, and so on composite populations was really interesting.
Yeah, for sure. So then you move into beef genomics in Australia and you fall into the Northern Genomics Project, or rather you commence the Northern Genomics Project with Dr. Jeffrey Fordyce and Dr. Shannon Spate, also on the call. Shan, do you want to give us a little bit of an overview of what happened pulling this project together?
Yeah, well, yeah, Ben was the immaculate brainchild. And so basically what we did was looked at traits specific for Northern Australian cattle as a multi-breed genomic selection tool. So having a look at something that could work for your straight breds like your Brahmans and your Santas, but also of everything from composites to first crosses to, you know, Mickey bulls up in the Cape. So I started with them and did a lot of, I guess, the data collection. And we, when I was involved in the project, probably did around 20 to 30,000 heifers involved. And then Elsie took over after me. But what we were looking at primarily, like the two, I guess, crown jewel traits we were looking at was puberty. So age at first conception or when they were likely to first fall pregnant, and P4M. Pregnant within 4 months of calving. So these are two main drivers of productivity in North Australia. So are we waiting for them to calve as a 2-year-old, 3-year-old, or, you know, in some cases 4 or 5-year-olds? And can they have a calf a year or something close to that? So we collaborated with a number of different sites that you can see on that map, everything in North Australia. So we defined that as Queensland, Northern Territory, and the top half of WA, and really focused on commercial herds and collecting these in commercial environments, which I think was a first for that scale project. And then I know we're going to dive into GBVs. So to explain a little bit about what they look like and what the outcome of the project was, is that effectively you're given a rank on these animals. So they can be ranked on a 1 to 100 percentile. So if you've got something like that example up there, with that weight in the 93rd percentile, that means that that animal is in like the top 7% for weight across the population, whereas something that would be like the ranking of 3 in those hip heights means that those would be probably pretty short animals or produce pretty short animals. They're in the bottom 3% for height. We've also translated these more widely on a scale of 1 to 5, or a very low to very high, as you can see here. So this quintiles basically gives a bit more, allows people to dive into the numbers a little bit more, and have more confidence in them as well, and see which are the real like top 20 percenters. So anything with a 5 will be in the top 20% of the population. Anything with a 1 will be in the bottom 20% of the population, and a 3 is effectively average. And it makes it a really easy tool for producers to have a look at like top and bottom performing bulls, because you don't have to keep on going back to a reference population line effectively. So in general, what people are looking for is more 4s and 5s, probably with the exception of hip height. 4s and 5s are your tall animals. You're probably not after 1s or 2s potentially either, but you're kind of looking for that middle ground there. So we looked at those traits of weight, hip height, body condition score, puberty and P4M, which I went into, temperament, and then tick resistance and fly lesions, which are also very important for Northern Australian cattle.
Yeah. So to dive into it now, so if you've got any questions as we're going along, please put them in the Q&A section of the Zoom, and we'll come back around to them at the end. We're just going to hop right in. So a big question with the GBVs is using it for selection. And in the case of when we're looking at our heifers, we don't have a direct calving ease breeding value available. However, GBVs can be used to select heifer bulls, and I'll pass over to Ben to explain more of what he's seen in that regard.
Obviously, with your heifer bulls, you want to avoid really, really tall bulls with that very tall or big height genetics. So you're looking for moderate height GBVs, 2 or 3s, and also moderate weights. But you do want to have a focus on fertility. So you have fertile heifers born from these bulls. So looking for heifer puberty GBVs of 3 and above, and also P4M, so that your genetics for rebreed is really good.
Yeah, awesome. Moving along with selection. So there are cases where we're starting to see GBVs and EBVs presented alongside, particularly by seed stock producers. Will you talk to us a bit, Ben, about how you're seeing these correlate or not correlate, and why is that happening?
So just to go back a bit, GBVs were really developed to fill in a gap. So we obviously have this wonderful EBV system for our purebred cattle, and they're working really well in the south. They've got very strong genetic trends for things like marbling, weight, and so on. But in the north, there was a very clear gap for multi-breed cattle, composite crossbred cattle, and also in some respects for the fertility traits. We do have days to calving for some breeds, and that's a wonderful trait when you've got EBVs for days to calving. But GBVs were really to fill in the gap that existed for northern cattle. We have done quite a bit of work looking at the correlation of GBVs and EBVs. To what extent do they tell you the same information? The correlations between them are reasonable. They're not amazingly high, and there's a reason for that. And that is because neither the GBVs or the EBVs are 100% accurate. And as we'll come to later, a set of GBVs might have an accuracy of 0.55 or 0.6. Your EBVs, depending on how much information is behind them, might have a similar sort of accuracy. If they both have an accuracy of 0.6, then the correlation between them is only going to be the multiple of those two accuracies. So the 0.6 times 0.6, which gives you about 0.3 to 0.4. That's the best you can expect. The really important thing, though, is not actually the correlation between the GBV and EBV. It's what the correlation with the true breeding value is. So do these tools let you truly select the best animals? And with an accuracy of about 0.6, you can certainly start to identify the top groups of animals. Sorry, Elsie, I'm probably jumping ahead a bit to where you were going, but with 0.6, you can certainly identify the top groups of animals. It doesn't mean every animal you select with a high GBV is going to turn out to be a winner once that bull has lots of progeny and so on. But the group certainly will have a high genetic merit. And we're going to show you, I think, some examples of that later on. And the same goes for EBVs as well. With an accuracy of about 0.6, it lets you pick out that top group. So they're both tools are letting you pick out that top groups with good genetic merit.
Yeah, so you're saying that sometimes they may not agree because neither tool is 100% accurate, but it comes back to using the tools available to build a bull team that is going to do the job that you need them to do.
Yep. Because they're being calibrated in different reference sets, that's why they don't agree perfectly. If you are using both, if a bull comes up high on GBV and on EBV, fantastic.
Yeah, that's awesome. All right, so then when we go back to looking at the GBVs, how are we seeing the correlations between the 8 traits that we have there, and how does that inform how we select animals?
Yes, so I think the most interesting correlation that comes through is the negative correlation of fertility with height. And I think this is actually quite important in the north. I think in the past, there has been some selection just for height of animals. And unfortunately, that is negatively correlated with fertility. We see that in the overall correlation. We can also see that for individual genes. We know some of the genes involved in fertility. And when we look into those genes, the genes that improve fertility, improve like puberty and P4M, they tend to be associated with animals of more moderate or shorter, more moderate stature. It's these really tall, skinny animals that have lower fertility. And some of you on the call might have personal experience of that, but that certainly comes through very strongly. So selecting just for stature or just for height is a bad idea because you're going to have quite a negative effect on fertility. That's really the biggest one there. The fertility traits themselves, puberty and P4M, they're quite favourably correlated. So heifers that cycle earlier are more likely to be the ones that successfully rebreed as well. So that's really good.
And so, Ben, how does that work with understanding, like if we take a broader look at genomics and having a look at chasing a number of different traits for genetic selection? Like, of course, we want high fertility animals, but we're selling into feedlots. So we also need animals that perform well in feedlots. And then we might be going into a value marketing chain where we need high marbling animals. How do we select with that in mind? How can GBVs help us?
I think the most obvious thing to do is to put weight or emphasis on the weight GBV and also on the fertility GBV, because you want to improve your weights and you want to improve your fertility. And the nice thing there is the correlations are pretty weak. If anything, they're favourable for weight and puberty. So if you select those heavier animals, this is for 600 days, they're more likely to be the ones, slightly more likely to be the ones that cycle early. And there's not much correlation there at all at P4M. So you can certainly select for both those traits without having an adverse impact on either.
And so how does heritability come into the mix when we're applying this kind of selection pressure across these traits?
Yep. So this is the heritability table for our different traits. And just to explain to people what this means, the heritability is out of all the differences you see between your animals in a trait, what proportion of that is due to genetics. And we can work that out in our data set because we have this snapshot of their genome, the SNP chip data. So for example, for puberty, whether they're cycling or not by 600 days, 22% of the differences in animals is genetics. For P4M, it's 10%, that's lower, and that's because there's more management impacts. That doesn't mean you can't select for it though. It's easier to make really rapid gains for a trait with high heritability, and the classic is height. You see that heritability is really high. So it's really easy to visually select and make very rapid gains for that trait, unfortunately, and that is part of what's happened. If the heritability is lower, you can still certainly make gains, but they can be a bit slower. It doesn't mean there's not genetic variation there. It just means the environment and management and so on has a big impact. But certainly in dairy cattle, the fertility traits in dairy cattle have an even lower heritability, and they've made quite substantial gains recently. It's interesting looking at a couple of the other traits there, like temperament and tick score. They have quite high heritabilities. So that means you can make quite rapid gains for good temperament and more tick-resistant animals.
So lower heritability traits, we're looking at just extend your timeline on expectation of results if you have that kind of continued pressure. So something like P4M or puberty is more like a generational goal potentially, whereas something like temperament and height, you could change quite rapidly.
Yes, basically, yes. You can still make good gains for P4M if you put a lot of emphasis on that trait. For example, if you only selected the 5s and the 4s, you would still make good gains, but certainly slower than some of the other traits.
Yeah, wonderful. I think we're swinging back to accuracy, and I guess this is a question that we often get is with a 0.5 accuracy or a 50% accuracy, isn't that just like rolling the dice or, you know, flipping a coin? So if you could explain kind of exactly how accuracy plays into it and why 0.5 is actually quite a good accuracy. And then a follow-up as an extra bonus one was like, how do we get to a 0.8? And do you believe it's achievable in the beef industry?
Yeah. So if we're flipping the dice, that would be an accuracy of 0. That means you've got no information on the animal and you're just guessing. If you've got an accuracy of 1, it would mean the GBV is telling you perfectly what the genetic merit of that animal is. So an accuracy of 0.5, 0.6 is intermediate to that. And basically what it means is if you pick a group of high GBV animals, you're going to pick on average good animals, but there'll definitely be some movement as those animals get progeny and accumulate more information. But 0.5 to 0.6, that's definitely high enough to start picking groups of bulls or groups of heifers to retain, or as you've got written there, to start screening out the real duds, so to cull out the 1s and 2s. In the dairy industry, sorry?
No, you go. Okay.
In the dairy industry, we're up to accuracies of 0.8, as you mentioned. That means you really can start to pick winners, and that's what people are doing. So the ones you pick out on GBV are nearly always going to be the very top genetic merit animals. So you don't have to worry so much about groups anymore. That's a really nice situation to be in. How do you get there? Just lots of data. It's not very inspiring or innovative, really. It's just collecting more and more data to increase those accuracies.
That's the fun task ahead of us.
Yes.
So we have a question from the crowd that's actually very relevant to the current topic. So the question is, when we're looking at the rankings versus the percentiles, the rankings versus the quintiles in selecting animals, and we're comparing between an animal that's, say, a ranking of 85 or 95, is it that important when it's sitting in that close range, or are we better off at the moment looking at the quintiles, the 1 to 5s, when we're selecting for animals, because there's just not that much movement when we're looking at the rankings?
Yeah, so we might show later on a graph that shows if you select animals that are all 5s, the genetic merit of that group on average is very high. So the average GBV of that group is very high.
Yeah, so basically if they're a ranking of 80 or over, they're the equivalent of a quintile 5, and therefore... Yeah. I think so. I think the difference really with an accuracy of 0.5, 0.6, the difference between 0.85 and 90 may not be that much in practice. But certainly if you look at the quintiles,
there's a big difference between a group with quintile 1 and a group with quintile 5.
Yeah.
All right, so
Oh, that's exactly this.
yeah,
Yep.
we'll hop into Ben's graphs now. So this is the GBV validation. Ben did these in February when we updated the reference herd to add another 10,000 animals. So this was the beef CRC herd validation. Take it away, Ben.
Yep. So what we wanted to see was indeed for these 5s to 1s, how accurately were we predicting the average of the group of animals? And the data I used here was from the beef CRC. Some of you may remember that. And there are actually 1,000 Brahman heifers that were followed through their lifetime. And there were about 1,000 tropical composite animals as well. And they got really detailed information. So the heifers were actually scanned every 6 weeks or so to record what age at puberty, when they went through puberty. And what this graph is I worked, because those animals were genotyped, I could calculate the GBV for those 1,000 Brahmins and those 1,000 tropical composites. And then I could work out what quintile each heifer sat in. So in quintile 5, for example, there might be 80 to 100 animals. In quintile 1, there might be 80 to 100 animals. And then I could look for puberty GBV quintile 5, so the best 20%, based just on the DNA marker, the GBV prediction. What was their actual age at puberty for that group? And you can see for the Brahmins, it's about 650 days. For the trop comps, it's about 600 days. You compare that to the 1s. So this is the worst 20% predicted just with the DNA markers. When you look at their actual age at puberty for that group, for the Brahmins, it was almost half a year later, 750 days. For the trop comps, it was nearly 700 days. So there's a big difference there. And I've worked out the error bars on that. It's a very significant difference.
Yeah.
So the GBVs, when you pull apart those animals by quintile, they're really showing up with a very different age at puberty.
Mm-hmm. And, you know, that's sort of contributing to, that's an extra calf in a lifetime of a cow, isn't it?
Yep. If they go through puberty that much earlier for the 5s compared to the 1s. Yep.
Yeah, quite significant.
Yep.
And this is the P4M for the Brahmins.
So this is looking at, for those heifers after they've had their first calf, what proportion of the heifers in each quintile are pregnant. So got pregnant while they were lactating. So again, for P4M, pregnant or not, 4 months after calving, we did the GBV prediction and grouped the animals into quintile 1 being the worst to 5. And you can see a big difference there again. So for the 1s predicted just with the DNA markers, when we looked at in this group of CRC animals, how many were actually pregnant while lactating, there was only 36. While for the 4s, there were 67% were pregnant 4 months after calving. So that's a really substantial difference. For the Brahmins, there actually weren't any 5s in this data set. There were no Brahmins coming up with the top fertility in this particular data set.
Yep. How many cows were in this data set, Ben?
So this is 1,000 cows. Yep. So it's quite a substantial data set.
Yep. And the same.
And the same for the trop comps. There are about 900, I think, 1,000 to 900 in this data set. And you can see the big difference. So the GBVs 1s predicted just on their DNA markers, only 20% of them got pregnant within 4 months of calving, while for the 5s, 69% were pregnant. So there's a really big difference there.
And do you want to explain our little glitch on the number 2?
So this is what happens when you analyze real data. There's obviously a finite number of animals behind this, so it's not perfect, and our accuracies aren't perfect either.
Yeah. The way I like to look at this too is looking at, on the genetics alone, this is the preg test rates that you're looking at. So then for poorer genetics, your environment and your management has to make up so much more in order to get a decent preg test rate. So if you're aiming for 80%, you've got a lot of work to do if you've got P4M1 cows versus P4M5 cows. So that's sort of how I see it in everyday application when you start to bring the environment into the mix. The tick GBVs, and this is Bos indicus content, the horizontal axis here.
So this is partly to demonstrate Brahmins do have some really good traits.
Yeah.
So this is our tick GBV, and what I've done here is just lined up the GBVs against Bos indicus content. So 100% would be high Bos indicus content Brahmins, purebred Brahmins. 0 would be something like your Angus or Herefords, Bos Taurus. And a higher GBV is more susceptible. This is based on tick scores. So the higher the tick score is, the more ticks they have, the more susceptible they are. And you can see the 0 content animals, so the Bos Taurus, purebred Bos Taurus, they're getting quite high GBVs, so big tick scores, very susceptible. Whereas the high content Brahmins, 100% Bos indicus, their GBVs are much lower.
Yeah.
So that, if you put it on the quintile scale, these are the really good ones. They would be getting 5s. They're very resistant. The ones, the Bos Taurus ones for ticks, are the susceptible ones that are getting a 1 for your quintiles. Yep. So it's important to remember for the north that traits like tick resistance obviously are pretty important in some places.
Yeah, absolutely.
On a similar note, if you jump back, Elsie, we do have a kind of similar question from the crowd in terms of how do, I guess, Brahmins, or like maybe we broaden it to Bos indicus content versus lower Bos indicus or Bos Taurus content measure up in terms of body condition score. So we know that body condition score kind of, we've shown it's like an adaptation, or like a, how well do they do through the tough seasons? Do Bos indicus perform better on that? I know we don't have a chart to back it up, so I don't know if you can reach into the depths of your memory.
So we actually have, what I'll do is get back to, we can post it on the website or something, but that's a good thing to look at. I haven't actually done that one, so I better do it before I come up with an answer.
Yeah.
It's a good question.
No worries. Then I think we're moving on to heterozygosity, which we might be losing an image behind for some reason.
It's not playing with me. If I take it back out, you can see it, but you can see all my side stuff as well.
There we go. Well, maybe that's all right for now. But basically, so with RePRO BI, we do look at the breed composition. And part of this being the heterozygosity. What does that mean for selection, and what should we be aiming for? What does this number mean? How should producers be using it?
So this number is basically how much, so obviously animals get 1 copy of the genome from their mother, 1 copy from their father. So we get the same thing as humans, and cows get the same thing as well. This number really measures how different the genomes the animals get from the bull and from the dam are. Just to calibrate it, it's actually the marker heterozygosity, so how many differences we see in the SNP marker genotypes. It goes from, if you had a really inbred Wagyu, it might be 0.25. Is about as low as it gets. And if you had an F1 Brahmin Angus cross, which is about as outbred as you can get, it would be 0.5. So inbred animals have 0.25, really outbred F1 crosses have 0.5. So heterosis, of course, is a wonderful thing. We actually analyze these using this data for body weight. I think by 600 days, it can be an extra 40 to 50 kilograms as a result of the heterosis from crossing an Indicus and Taurus animal. So it's a really good thing.
And so that's where we hear the word hybrid vigor coming in.
This is exactly that 40 kilograms is the hybrid vigor, and it's big for weight. It's even bigger for fertility when we look at that. If you've got a Brahman Angus cross, they'll go through puberty much earlier, be more likely to get back in calf while lactating, and so on. So it's a really good thing. The trick for us in the GBVs is we actually have to remove that heterosis when we do the analysis, because we want the bit of genetics that is passed on to the progeny, just that bit that accumulates over generations. So we actually have to take that heterosis out. But if you're producing beef and so on in the north, it's obviously a really good thing to try and capture. And you can look how much heterosis are you actually capturing. The closer that number is to 0.5, the closer you are to getting to your maximum heterosis.
Yeah. So it's an extra boost, but just for one generation.
Yes. Obviously, if you create an F1, the question is, where do you go next?
Yeah. Wonderful.
Does heterosis boost fertility as well as?
Yes, absolutely. I'll see it has a really big effect on fertility. Yep.
And that's reflected in the GBVs because we take it out. So that could be
it's not in the GBVs. But what you will see is the composite animals have a higher heterozygosity.
Yeah.
So in your composites, the reason for creating composites in part is to capture that heterosis. So you can actually see that in that number. They'll often have a heterozygosity of about 0.4.
Yep. And then one final one from me before we pass it to the floor, but where do you see the future of genomics in beef and particularly in Australia or worldwide, I guess, for that matter?
Yes, so I think the first place we'll go is adding in more traits. And we've actually just finished a big project on eating quality with MLA, where we recorded 9,000 steak samples were eaten by people in Australia, but also Ireland and the USA. And all those animals where the steaks came from were genotyped. So we have quite good predictions, GBVs, for tenderness, juiciness, overall liking, and so on. So I think to have those measures of meat quality, along with marbling, would be really good. And then the other place to go, there's two other places to go. One is for disease resistance. And we've been working on a bovine respiratory disease, GBV, at the moment just with Angus, but it could be expanded. And the other one is sustainability. So methane could be factored in there.
Wonderful. Sounds all very exciting. Are you willing to take a punt on when they would be available to your everyday producer? In a scheme of years, are we looking at 10 years time, 5 years time?
No, a year or two, I would say.
A year or two. That's very exciting.
That is awesome. Do we have further questions from the crowd? Can we get you to put them into the comments or the Q&A? Oh, here we go. Do you think there is an issue with crossbreeding getting so complex now for a lot of producers? Have we gone so far from hybrid vigor? Like, should we be simplifying the breeds?
I am very sympathetic with the question. I think it is complex to run systematic crossbreeding schemes. It is very hard. Just anecdotally, my parents have a property out near Warwick, and they've sort of been trying to run systematic crossbreeding schemes, and it's actually quite hard to maintain some of them. I think the composites, where you capture some of that heterosis, is a very good idea. I think with all this talk of genomic selection, EBVs and GBVs, it is easy to forget about how much of a benefit heterosis can be. So I think it's important not to lose sight of that. But I think probably the composites are the most practical way of capturing that.
Yeah. Okay, cool. I'm just going to share my screen again for this next question. So the question is, has there been enough data collected on all traits for them to be useful enough to select on? And I think that's looking more at the tick and fly resistance. So previously we've not had huge data numbers, and I've just shared the screen now for where we're looking at the current data numbers. Temperament's another one that's quite low. So what would you say about selecting on those traits using genomics?
Good question. Got a lot of confidence in the puberty. P4M's looking really good. We validated those traits in multiple different ways. The tick score, we've sort of nearly doubled in the latest run the number of records behind that. I think that's starting to look pretty solid. The validations that we've done look good. The fly, it does validate when but I'd like to do more work there. And given it could potentially be such an important trait, given the perhaps that some chemicals won't be able to use for fly and so on. I think breeding for fly resistance is a great idea, but it would be great to have more records for that, no doubt about it all. I wouldn't put all your weight on the fly GBVs at the moment. You might cull out some of the really susceptible ones, the ones and so on. Yeah.
And is that also influenced by the fact that fly is a lower heritability as well?
Yeah, oh, absolutely. Sorry, I should have said that, Elsie. Yeah.
No, yep. And then the higher heritability traits, like for temperament and tick score, even though they're smaller data numbers, the higher heritability means that we don't need as much data as lower heritability traits.
That's true. Yes. You have to be a bit careful though, because there's another angle in there in that to make it really useful across multi-breeds, you need sample or records from animals of all those different breeds. And I think for tick score, we're starting to get that good coverage. For fly, it'd still be nice to have more records.
Yeah. Awesome. Any more questions from the audience? Otherwise, we'll wrap up and let Ben get back to his millions of jobs. All right. If you have further questions following the webinar, please get in touch with us. Always happy to answer questions, and if they're super tricky, we'll of course forward them on to Ben to get the brains trust in on them. Thank you so much for your time today, Ben. We really appreciate it. Having you backing this tool is really important to us, and hearing about the science that's gone in behind it is amazing. So thank you so much for your time today, and thank you everyone for joining us.
Thank you, and thanks to everybody online. Great to talk to you.
Thanks, guys.